I see that you are working with the VotingRegressor, specifically using soft voting. This means that each individual regression model, linear regression, support vector regression, and random forest regression makes its prediction. Then, I simply average these individual predictions to obtain the final prediction of my VotingRegressor. It's a straightforward average, not a weighted one. Think of it like this. If the models predict 10, 12, and 15, my VotingRegressor predicts 10 plus 12 plus 15. 3 equals 12.33. This is the final output of the VotingRegressor. After I have obtained the predictions from each of my individual regression models, LR, SVR, and RFR, I will average them using the soft voting approach as described in the previous step. This average value constitutes the final prediction of my ensemble model, the VotingRegressor. It's a simple average, the magic of ensemble learning. This is one of the 3 individual regression models that I am using in my ensemble. LR aims to fit a linear relationship between my predictor variables and my response variable. It's a simple, yet powerful method for regression. SVR is another model I am using. It finds the optimal hyperplane that best fits the data points while maximizing the margin of separation, minimizing prediction errors. It is very versatile, capable of handling nonlinear relationships using kernel tricks. It's a different kind of approach from LR. This is my 3rd regression model. It is an ensemble method itself, averaging the predictions of many decision trees. Each tree is trained on a subset of my data, and averaging across them reduces variance, improving robustness. It's a powerful method to increase performance. I'll explain soft voting in VotingRegressor. Imagine you have 3 friends, each predicting the price of an apple. Soft voting means I simply take the average of their predictions. No fancy weighting involved. It's a simple average. That's how VotingRegressor works with soft voting. I'm using a linear regression model. It assumes there's a straight line relationship between the input features and the output variable. Think of fitting a line to data points. I'm using a dataset, the training data, to train each of my 3 models: linear regression, support vector regressor, and random forest regressor. It's the data they learn from to make future predictions. This one's a support vector regressor, and it tries to find the best boundary to separate data points. Think of it as drawing a line, or higher dimensional hyperplane, that best represents the relationship between your data. Each of my 3 models makes its own prediction. That is, linear regression gives me its prediction, support vector regressor gives me its prediction, and random forest regressor gives me its prediction for the same input. After each model makes its prediction, I combine them using soft voting, which means simply averaging the predictions made by each of my 3 models, to get a final result. This is how I make my final prediction. I am also using a random forest regressor. It combines many decision trees to make a prediction. Think of it as a group of experts each voting to get the final decision. This is different than support vector regression and linear regression models that I use. I use this data to train 3 different regression models: linear regression, LR, support vector regressor, SVR, and random forest regressor, RFR. Each model gets the same training data. This is crucial because we're comparing how well each model, and then their combination, performs. It's like giving 3 chefs the same set of ingredients to see who makes the best dish. The VotingRegressor is an ensemble method. That means I combine multiple models to get a better result than any single model could produce on its own. In this case, the 3 models I trained earlier are combined using the VotingRegressor. I use a simple average of their predictions to make the final prediction. It's like getting a group opinion instead of relying on just one person. This is one of the 3 individual regression models I'm using. SVR stands for support vector regressor, and it's a powerful technique, but sometimes it's too sensitive to noise or outliers. I am using it within the VotingRegressor to hope that its strengths are balanced out by the other's strengths. Another model, linear regression, LR, is one of the simplest models. It works by fitting a straight line to the data. It's easy to interpret but can be very basic, not very powerful for complex relationships. I'm using it in my ensemble to offset some of the limitations of other models. After training each of the three models, LR, SVR, RFR, I use them to make predictions on new data. Each model gives me its own prediction. These predictions are the input for the VotingRegressor. They are combined to form the final prediction. I use the simple average of those three individual predictions. The VotingRegressor combines the predictions by averaging them. This approach is called soft voting. No special weighting is given to any of the individual predictions. It is simply averaging them equally. This is the ultimate outcome, the prediction the VotingRegressor gives after averaging the predictions from linear regression, support vector regression, and random forest regression. I hope it is more accurate than any single model could achieve alone. I'm using the same dataset to train each of the three different regression models: linear regression, LR, support vector regressor, SVR, and random forest regressor, RFR. This ensures a fair comparison when I evaluate the performance of the voting regressor, which combines these models. The voting regressor, when using soft voting, takes the predictions from each of the three individual models, LR, SVR, RFR, and calculates a simple average. It's a straightforward mean of the predictions. Think of it like this: if LR predicts 10, SVR predicts 12, and RFR predicts 8, the voting regressor predicts 10 plus 12 plus 8, 3 equals 10. The final prediction of the voting regressor is the result of the averaging process I just described. It's a single value that's meant to be a more robust prediction than any individual model might produce on its own. This is one of the three regression models used in the ensemble, and it's a powerful, versatile model. This machine learning model is great at finding patterns in the data even if the relationship between features and target variable is complex. This is another model among the three in my ensemble. This model is an ensemble method itself, a collection of decision trees. It usually excels in its performance, providing excellent accuracy. This is a straightforward model where I find the best fitting straight line, or hyperplane in multiple dimensions, through the data. It is used as one of the three regression models I'm putting together. I'm building a voting regressor using three different regression models, LR, SVR, RFR. The architecture is simply a combination of these models. Their predictions are combined through the averaging process. I see that statement A is about how voting regressor makes predictions. It says the final prediction is simply the average of what each of the three models, linear regression, support vector regressor, and random forest regressor, predict individually. That's exactly what soft voting means in this context. It's a simple average, not a weighted one. Statement D gets to the heart of why we use ensemble methods like voting regressor. The idea is that by combining different models, each with its own strengths and weaknesses, you can get a better overall prediction than any single model could achieve on its own. Think of it like this: one model might be great at spotting certain patterns, while another excels at something else. Combining them can improve the chances of capturing all those patterns accurately. Statement C is incorrect. I want to clarify that standard voting regressor, using soft voting, as mentioned in the question, does a straightforward average. It doesn't give more weight to a model that performs better than another. That's a key difference to remember. This statement is false, too. While a voting regressor often improves accuracy, there's no guarantee it always beats the best individual model. It's possible one model is so exceptionally good that averaging it with others actually reduces performance. So, it's a probabilistic improvement, not a guaranteed one. This is one of the three regression models used in the voting regressor. I'm mentioning it to provide the complete context, since it's a part of the problem context. This is one of the three regression models used in the voting regressor. I'm mentioning it to provide the complete context, since it's a part of the problem context. This is one of the three regression models used in the voting regressor. I'm mentioning it to provide the complete context, since it's a part of the problem context. This refers to how the voting regressor combines the predictions of the three different regression models. It's an ensemble method that leverages the strengths of multiple models. This describes the specific way the voting regressor combines predictions. Soft voting means a simple average of the predictions. This sets the stage for the quiz question on understanding the function of a voting regressor. This is the final prediction output by the voting regressor, which is the simple average of the predictions from the three base models when using soft voting. I see this as the heart of the VotingRegressor with SOFT voting. I'm taking each prediction from linear regression, support vector regressor, and random forest regressor and calculating a simple average. Think of it like this: if the models predict 10, 12, and 15, I average those to get a final prediction of 12.33. This is my simple average and my final prediction for the VotingRegressor. This is one of the three regression models I use in my ensemble method. SVR is a powerful and widely used machine learning algorithm from Sklearn that aims to find an optimal hyperplane to separate the data and make predictions. I use the SVR prediction as one of the inputs to my VotingRegressor. Another key model in my ensemble. The RFR uses an ensemble of decision trees to improve the prediction accuracy. I'm leveraging its strengths to generate another input prediction for my VotingRegressor. Each tree in the forest votes for a prediction, and the most common vote becomes the prediction. This is the classic least squares approach. Given the features, it finds the best fit line to predict outcomes. It's another model whose prediction forms part of the input data in my voting regressor. The simplicity and speed of LR are excellent complements to the complexity of SVR and RFR. This is the final output of my VotingRegressor. I obtain this prediction by averaging the predictions from the linear regression, support vector regression, and random forest regression. It's a combined prediction that aims to be more accurate than any of the individual model predictions. This refers to the overall structure of my ensemble method. I'm combining three different regression models: linear regression, LR, support vector regressor, SVR, and random forest regressor, RFR, to create a more robust and potentially more accurate prediction model. Think of it as a team effort, where each member contributes their expertise. My team here is my ensemble of regressors. Each member's output, prediction, influences the final output. This overall combination is my voting regressor architecture.